Hello, everybody. Good morning, good afternoon. I guess I can say that still. I think good evening will be a little bit of a far-fetched for most of this session, but thank you very much for joining our Neo4j GraphRAG virtual workshop today. This nice morning, at least from here from Germany. It's a very sunny day, so I'm happy to have Alex Thomas and Will Tai as our two hosts and trainers for today. So thank you all for joining them. Thank you, Will and Alex, particularly already before we even started, that you are doing this workshop with us, that you prepared the material, and that you are giving us this very insightful session today. I'm, very happy to see all of you joining. So it's really great to see you there. We have a public chat that is open, so you can talk to us, you can ask questions, or say hi from wherever you're watching and what the weather's like. There's a Q&A segment as well, which you should be using preferably if you have any questions, if anything is unclear, if anything doesn't make sense to you. Please use that. It's a little easier for us to follow your questions there, and then we can answer them and see about to solve any issues that arise during the session. We will have a couple of breaks during the workshop today. So if there are a couple of questions that we think are interesting and we should answer in public, then we can take these break points and look into those. Otherwise, we'll follow through as we go. I think usually that works well. The point is to be interactive. The point is to be, following along from your side. So we will share a couple of links. We will also share an OpenAI API key that you can use for this workshop. Obviously, only for this workshop. But while the workshop is running, you can use that. You don't have to use your own. But it is the point to have an interactive session. So please, if you want, if you can, follow along and join the workshop. The session, as I said, will be recorded as well. So we will be sending you the link to this video afterwards. So if you have any reasons to stop off early, or if something wasn't quite, maybe a little bit too quick, maybe you want to rewatch it again, you can, and we will send you the link to the video, to all the other materials as well in an email afterwards. So you can completely focus on what's on screen today and don't worry about something like videos or slides. Yeah, I see people from Rome. Hi, Lucy. Martin from Munich, Vash from Cambridge, David from Dorset, also the UK. So great to see you all. Great to see you join. I'm very happy. I'll be off camera most of the time, but I'll be around. I'll be in chat. If you have any questions, anything, I'll try to answer, or at least collect as much as possible. And then, as I said, we will take the time to answer a couple of questions during breaks. But yeah, I think with that out of the way, I would like to officially hand it over to Alex and Will. Again, thank you very much for you two to be here. I'm looking forward to this GraphRAG virtual workshop today. And yeah, wish you all have a good session. Have lots of fun and enjoy the morning.
All right. Thank you, Alex. Yeah, good morning, good afternoon, everyone. Welcome to this workshop. I'm Alex. I'm going to be taking you through the first hour of the workshop today, and then handing over to Will for the second half. So yeah, the purpose of this workshop today is to take you through the basics of GraphRAG and to get you building some basic GraphRAG applications using Neo4j's Python package. So like I said, this course is going to be run in two halves. I'll be taking the first half, and Will will be taking the second half. And this workshop is going to be following along a Graph Academy course that we have here. It's going to be hands-on, so there's going to be some sections where I'm going to be taking you through some concepts and some and sort of describing some of the basics of GraphRAG to you. But then there's also going to be some sections where we're going to be writing some Cypher and some Python, and we're going to be running some exercises to sort of illustrate those concepts. So, like I said, this course follows along, this workshop, follows along a Graph Academy course. So I'm going to post the course in the chat for you now. So if you want to follow it along at the same time and complete the course as I do, then feel free. We're also going to be using OpenAI for this course. So I'm going to post in the chat an OpenAI API key that you can use for the purposes of this course. This will be deleted at the end of the workshop today. But for the next 2 hours, you can use this to complete this GraphRAG Graph Academy course. Okay. With that out of the way, let me share my screen and we can get started. Okay. So once you have signed up for the Graph Academy course, you should see a page like this. The course is sort of split into two. So I'm going to be taking the first half. And in this first half of the course, I'm going to take you through some of the sort of basic concepts that lie behind GraphRAG. So things like vector indexes, full text indexes, knowledge graphs, and some of the basics of how we can get our data into Neo4j for our GraphRAG apps. But before we dive in, like I said, this course is hands-on. So there's going to be some coding. There's going to be some coding parts to this course. So you will need to set up a development environment if you want to follow along with those coding parts. So there's two ways you can do this. There's develop on your local machine. So you can clone our Python repo, our GitHub repo here, and install the Python requirements once you've downloaded that to your local machine. Or when you sign up to this page, when you click on this page, you should see a button here for opening GitHub code spaces. What this will do is this will create a virtual machine on GitHub for you and install the dependencies automatically. And you can just work from that if you want to develop on GitHub. But I'm going to be doing this locally, so I'll just take you through how we set up the development environment locally. So if I go over to my VS Code instance here, sorry, apologies. I was meant to share my entire screen. So go over to my VS Code instance here, where I've already cloned the repo. What you need to do first, like I said, is you need to install these requirements here. So once you have cloned this repo, you do pip install requirements. I won't run this now because I've already done it. It does take a couple of minutes, so don't be worried if it's a bit slow. The next step after you've installed the requirements in your local development environment is to set up an .m file. So you should see a file like this called .m.example. When you clone the repo, what you want to do is you want to copy this file and rename it to .env. And then what we're going to do is we're going to copy some values in here. So once you've created this .env file, you want to copy the OpenAI API key into this first line here. So I've already done that here. And then we're going to copy some details about the Neo4j instance that we're going to be working with. So if we go back to the Graph Academy page, What we'll see down here is some details about the Neo4j instance that we're going to be working with. So we have a URI, a password. So all we want to do is we want to copy those, and we want to paste the URI in here, the username in here, and the password in here. So once you have that, once you have those requirements installed and you have this .env file set up, you can test if everything's working by running Python test environment. And you should see run 5 tests in a certain amount of time. Okay, if you see the same thing or something similar here, your environment's okay, and you should be okay to follow along with the rest of the course. Okay, back to the GraphRAG Academy course. If you have any questions about setting this up, please post them in the Q&A section. I'm sure Will and Alex can help you with any difficulties you're having setting up your development environment. And like I said, you can use GitHub Codespaces for this as well, if you want to. Right. Onto the first section here. So in this section, we're going to cover vectors and embeddings, which are two concepts that are core in RAG. So firstly, what are vectors? Vectors are simply a list of numbers. They can be used to mathematically represent many things in the real world. For example, we have a three-dimensional vector here, which represents a point in space. And vectors can also be used to represent many different types of data, including text, images, and audio. And in RAG, we typically use vectors with very high dimensionalities, so thousands sometimes of dimensionalities. So not necessarily just a three-dimensional vector here, but thousands of numbers to represent text, audio, video. So what are embeddings? Well, when we talk about vectors in the context of machine learning and AI, we typically call vectors embeddings. Embeddings are just vectors which represent complex pieces of information, such as text or images. For example, here we have a embedding which represents the word apple. Typically in AI applications, we use specialized machine learning models called embedding models to create embeddings from our data. There are many types of these models available, which work with images or text in many different languages. These models represent each word or phrase in the data with a vector that captures its meaning. So what is semantic search? So semantic search is a very common use case for embeddings in machine learning systems. Semantic search allows someone searching a database for text, which is semantically similar to. Sorry, start that sentence again. So semantic search allows someone searching a database with text to find text in that database, which is semantically similar to their search query. So, for example, the phrase "big boats" is semantically similar to "large ships," even though both phrases contain completely different sets of words. And the way semantic search is done in RAG applications is using embeddings. Each piece of text in a database is typically indexed with an embedding, which captures its meaning. And then when a user searches, their search query, such as big boats, as the example I gave, is converted into an embedding and then sent to the database. This database then compares this vector with its list, with its index of vectors, and finds vectors which are close to it in some way. The database then uses this index to return the text associated with each of these vectors. So, for example, in this example, the database would return something like large ships if that was in the database. And below you'll find a few mathematical details about how this process works if you're interested, but in the interest of time, I'm going to skip that section. So now we're going to try semantically searching a Neo4j database containing some information about movies. We can see some examples here. So what I've done here is I plotted some of the movies in our database. So you can see we have Toy Story, and then description of Toy Story, Jumanji, description of Jumanji, Grumpy Old Men, Waiting to Exhale. You can also look at an example for an individual movie if you like. So here I'm just getting the details of Toy Story, but if you want to find the details of another movie, just update this string here. So embeddings have already been created for this challenge. They've been created on the plot lines of each of the movies. So these strings here. So let's first see an example of the embedding that was created for Toy Story here. So we want to see an embedding that represents this string. Oh, sorry, that was the wrong one. There we go. You can see here, this is the embedding for the plot line. Toy Story, this is the plot. So this vector here represents this piece of text here. Now, if we want to find other movies in the database with similar plots to Toy Story, we can compare this embedding to the other embeddings in the database using the next snippet. So this one here. We can see that Toy Story's plot is most similar to itself. So what we have here is we have the name of the movie, the plot, and how similar, as a score between 0 to 1, with 1 being the most similar, that plot is semantically to the plot of Toy Story. And as I said, we used the embeddings to calculate that score. So obviously, Toy Story's plot is most similar to itself. But we should see here a few other movies that have similar plots to Toy Story. The Never-Ending Story, Little Rascals, Gumby, Drop Dead Fred, and E.T. So again, feel free to try these snippets with another movie. So if you want to see which movies have plots that are most semantically similar to another movie, all you have to do is update this snippet here with the movie you want to try, and you'll be able to see the movies that are similar to, have plots that are semantically similar to the plot of that movie and the scores. Right. On to the next task. Okay. In the last challenge, we used our database of embeddings to compare movie plots to one another, and to find those which were most semantically similar to the plot of the movie Toy Story. In this challenge, we'll find out how we can create our own embeddings. As I mentioned a few lessons ago, in AI, typically, we used pre-trained ML models in order to create embeddings, which is what we'll do here. And we're going to use a embeddings model from OpenAI. So have your OpenAI key ready for this section, because we're going to copy and paste it into a few of the examples. Okay. So we can use the genai.vector.encode function within Neo4j to send requests to OpenAI's embeddings models. So let's start with creating an embedding for the text to create embeddings for. So we want to copy this into our browser over here. We then want to copy our OpenAI API key into here. And then we want to run this snippet. And what we're seeing here is the embedding created by OpenAI embedding model for the text to create embeddings for. And we can change this to something else, and we'll be able to see that the embedding will change. So there we go. It's changed. The numbers have changed slightly. Now, creating embeddings is cool on its own, but what we really want to do is use them to search our movies vector index. So we can do this by combining the function we used in the last section, the genai.vectoring.encode method, with the db.index.vector, with the db.index.vector.queryNodes method. Sorry, this is the one we used in the last section, and this is the one we used above. Right. So once again, what we do, we copy that into our browser. We copy the API key in here. And then we run our example. And what we're doing here is we are creating an embedding for the text, "A mysterious spaceship lands on Earth." We are creating that using the OpenAI model. We are sending that embedding to our vector index, and we're comparing that embedding with the embeddings associated with the movie plots already in our vector index, and we are returning the titles of those movies, the plots of those movies, and the scores, which have embeddings most similar to the embedding created for our string of text here. So what we should see is movies with plots that are most similar to "A Mysterious Spaceship Lands on Earth." Okay. So the movies we get are 2001: A Space Odyssey, Mysterious, obviously artificial object buried in the lunar surface. So kind of similar to our description here. We have Alien, again, spaceships, as sort of mentioned. Artificial intelligence, alien life mentioned in this one. Aliens. So all somewhat similar plots to our text here. Okay, to the next section. So we've seen how we can create embeddings and use them to search a vector index in a Neo4j database, but what if we want to create our own index? So we already have a vector index for the plots of our movies, but as I mentioned before, we can also use embeddings to represent images as well as text. So let's try creating an index for the posters of our movies. But let's take a look at the posters first. So you can see here, if we run this first code snippet, we'll get a link. We have Toy Story, and we'll get this link here, and this should take us to an image of the poster for Toy Story. Luckily, here we already have embeddings created for these posters. However, if you wanted to recreate them from scratch, you can do using the same process we used in the previous section. So these embeddings that we have already created can be used to compare images for similarity. So two images will have embeddings that are mathematically close, in the same way that two sentences will have embeddings that are mathematically close if they look similar. And we've used a specific image embedding model here to create these embeddings. So let's take a look at a poster embedding. So again, this embedding here, rather than representing some text, represents this image here. So now let's create our embedding, our index for these embeddings. We can use the create vector index command to do this. With this command, we need to include the name of the index we want to, the name we want to call the index. So we're going to call it movie posters here. Which property on which type of node we want to create the index on. So poster embedding here. This is the property that contains our embeddings. The dimensions of the embeddings. So these embeddings here have 512 numbers, and the similarity score. So this is mathematically the mathematical function that we want to use to compare our embeddings. So if we run our example here, we should see added one index. Now if we run this code here, we should be able to see if our index has been created. So we have our original movie plots. And yes, here we have our movie poster index. So now let's try using our index to find posters that are similar to the poster from the movie Babe. So this is the poster here for the movie Babe, and we're going to use our movie posters index to find posters that look similar to Babe. So if we run this example here, this is just using the same code that we used in the last section, in the section before, but we're just using the movie posters index here and the poster embeddings property rather than the plot embedding property and the movie plots embedding index. So what we're going to see here now is we're going to see some movies with posters that look similar to the poster for the movie Babe. So we have Babe, first one. Obviously, poster is most similar to itself. Let's see if any of these posters look similar. Like I said, this is the poster for the movie Babe. If we click on Lassie's poster here, you sort of see, yeah, it kind of looks similar to the movie Babe. There's a field, there's a nice sky, there's farm animals. Same with For the Rain. Sort of looks similar to the poster for the movie Babe. And we can view, and if you look, we'll get posters for movies that are and we've got posters for movies that are sort of similar to the movie for the for the poster for the movie Babe. But you can pick your own movie here. Like all you need to do is just replace this string here with the movie you want to see here. So, and then you'll be able to see which posters for that movie are most similar. Which other movies have posters that are most similar to the movie that you choose here? Okay. So if you remember from a few lessons ago, we used semantic similarity to compare two pieces of text and to see if they had similar meanings. For example, the two sentences, the child is playing with a toy and the kid is having fun with a plaything, are semantically similar as they share a similar meaning, even if they don't share many of the same words. Now, semantic search uses semantic similarity to find text with similar meanings to a user's query. However, semantic similarity isn't always the best measure to return the most useful, most relevant pieces of text for a user's query. So, for example, if we are searching for domain-specific terms, semantic search can fall apart. For example, semantic search may fail to return anything useful if you ask for like an unusual name of a character or a place in a movie, as it would have no way of knowing what this term means outside of its context. Like a good example query would be something like, which movie is set on Tatooine? Tatooine is a planet in the Star Wars universe. That query only has meaning within the Star Wars universe and won't necessarily return anything by semantic search if Tatooine wasn't seen and linked to the movie Star Wars in the training data of the embedding model. So the embedding model needs to know these specific terms for semantic search to work. And if it doesn't know the specific terms, if the embedding model had never seen Tatooine, for example, it might not find Star Wars when you search for Tatooine. Another example where semantic search falls down is when a user query includes specific strings that need to be matched, such as names or dates, in order for accurate results to be returned. So, for example, the query Oscar winners 2019. Semantic search might interpret the query broadly and return conceptually related results, such as notable films or discussions about the Oscars in general, but potentially from different years, focus on nominations rather than winners, when what we want for this query is only those winners for that specific year. So we need an alternative that allows us to deal with these issues, and full text search is one such alternative. Full text search matches queries on exact wording, including variations in spelling or grammar, rather than on semantic meaning. Full text search works by splitting the words in a user's query and comparing them with the words in a specific property on a specific node type, specific text property on a specific type of node. The database then returns those nodes with that specific text property, with the text, in that specific text property, which have the biggest overlap in words with the user's query. So, for example, this means for like a query like Oscar winners 2019, a full text search would return results containing 2019, and as such, containing exactly the string 2019, and as such might be more likely to return relevant results for this query. So any strings on any text strings in on these nodes that contain Oscar 2019, full text search is more likely to find them. Finally, there is a range of search methods which combine semantic and full text search in the hopes of harnessing the best of both of these techniques. We'll see an example. These techniques are called hybrid search. And we'll see an example of hybrid search in the second half of this workshop. So now we're going to try creating a full text index on our movie plot lines and querying it. Creating a full text index is very similar to creating a vector index. We just use the create full text index command rather than the create vector index command. And we just feed it the name of our index. So we're going to call it plot full text here. A type of node that we're going to create our index on. So we're going to create this on the movie nodes. And the properties that we want to create this index on. So we're going to create this on the plots. So this is going to be similar to, this is going to be an index on our plots here. So we run this, we should see I did one index. Now let's see if our index has been created. So if we run this again, you can see our plot full text index here. Now let's try querying the index. Again, this is a similar process to querying the vector index. We just use this function rather than the query vector index. So rather than the db.index.vector query nodes function that we used a few lessons ago. So we're going to be querying our plot full text index with the string 1375 Imperial China. Let's see, and we're going to be returning the titles of the movies, the plots of those movies, and the score associated with those movies. So what we're looking for here are movies whose plots are similar to this string. What we'll see here is we have the first movie is contains 1375 Imperial China. So like I said, in a full text index, what we're looking for are words in our query that have words in the index that we're querying over that contain the words in our query. So we can see here that this plot here contains all of the words in our query. So it gets the highest score. The scores in the full text index are not between 0 and 1, but they are ordered. So 11 is the highest score here, and that's why it's returned this movie. So this movie has a plot that is most similar to our query here. An extra challenge for anyone who wants to try it is to query the vector index, the plots vector index, the plots embeddings index, with this query, and to see what results it returns, and to see if it returns this movie and why it might not. Okay. Next, I want to talk a little bit about unstructured data. So unstructured data refers to information that doesn't fit neatly into predefined structures and types. For example, text files, emails, social media posts, videos, photos, audio files, and web pages. Unstructured data is often more difficult to analyze than structured data. We've already seen that embeddings are good at representing unstructured data, such as text. However, graphs are also a powerful tool for representing unstructured data. Graphs can be used to represent the entities and relationships within long pieces of text. For example, a graph could be used to represent the relationships between different products and customer feedback in a customer feedback system. Or a graph could be used to represent the various laws and regulations inside a legal document, for example. We call these types of graphs knowledge graphs. We'll also see later how combining vector indexes and graphs can help us build really advanced search processes, which can go a lot further than semantic search or full text search on its own. For the next few chapters, though, I'm going to talk about how we can build graphs from structured data and upload them to Neo4j. So first, chunking. When we deal with large amounts of unstructured data, chunking is often the first step when processing it. Chunking involves breaking a piece of text down into smaller chunks, which can then be more easily processed on their own. And this is a very common process when importing data into any RAG application. Text data is broken down into chunks. After this, the next step is usually to create embeddings for each of these chunks in order to be able to use semantic search with them. Chunking is also a first step in creating a graph from unstructured data, which can then be used in a RAG app. So like I said, we'll see how graphs can be used in RAG applications in the second half, but for now, we're going to go through the process of constructing a graph from unstructured data. So in this is the first of our coding challenges today. In this challenge, we're going to be using the Neo4j GraphRAG Python package to chunk a long piece of text and create an embedding for each chunk. So what we want to do is we want to go over to our IDE and we want to open this file. So in one-knowledge graph vectors, we want to open the create and embed chunks.py file. And this is where we're going to be putting our code. We're going to use the first paragraph for the Wikipedia article about London for this challenge, but if you want to use something else, all you need to do is just paste your text in here. First, we're going to chunk the text. So we're going to use a text splitter from our GraphRAG library. It's called the fixed size splitter. This text splitter splits a piece of text into chunks of 100 characters with an overlap of 10 characters between each chunks. And this is to avoid, the overlap here is to avoid sentences being split in the middle of each chunk. So with a good overlap, the idea is that at least one of the chunks should contain a full sentence. It can also be helpful when constructing the graph, as we'll see in the next challenge, to ensure that each chunk has enough content to extract the right entities and relationships. We'll see that in the next challenge. So what we're going to do, we're going to copy this code here. We're going to paste it into our editor. And then we're going to run it. And what we should see here is this text split into chunks. So you can see here, we have our text chunks. The first one here, London is the capital. The second one starts with a population. Third one at the head of the, the third one is 14.9 million. The fourth one at the head of a 50-mile estuary. So you can sort of see here how this fixed size splitter has split this big piece of text into separate text chunks. And you can sort of see how each chunk also contains a bit of the previous chunk. So the first text here ends with the population of, and the next one starts with population of, so it sort of starts with the last few characters of the previous chunk. Okay. Next, we'll create our embeddings for each chunk. So as I said, if we want to use semantic search with our data, we need embeddings. And again, we'll use OpenAI models for this. So we're going to use the text embeddings 3 large. If we copy this piece of code here paste it into our editor. What we're going to do is we're going to create embeddings for each of these chunks, and we're going to print out the first embedding. So we'll see an embedding that represents the first chunk here. So this one here. Go. This is our embedding. And you see it's quite a large embedding for this one. But this is the embedding that represents the first chunk from this piece of text. Okay, back to our course. So before we continue creating our graph, I want to go into a little bit more detail on knowledge graphs. As I said earlier, graphs are essential to many AI and machine learning applications. Knowledge graphs are a great way to represent the information contained in a particular domain. They provide a sort of structured way to represent entities, their attributes, and their relationships, allowing for a comprehensive and interconnected understanding of the information within their domain. And we can tailor our knowledge graphs for semantic search, data retrieval, and reasoning. And in the next challenge, we'll see how we can build a knowledge graph tailored for a RAG application. So you can see below here, there is a knowledge graph that represents Neo4j. Large language models can also be used to create knowledge graphs. If we want to create a knowledge graph from a piece of unstructured data, for example, such as a long piece of text, you first chunk this text up. Text chunks can then be fed to an LLM, which can then extract entities, relationships, and properties from it. And these can be used to populate nodes and edges in a knowledge graph. And we're going to see now how we can do that using the GraphRAG package. Okay, so we're going to go back to our IDE. And this time we're going to open up. I'm going to be in the same folder here, knowledge graphs vectors. I'm going to open up the build graph file this time. I'm going to scroll down, and this is where we're going to put our code. First, we're going to scroll to the very bottom of this lesson, and we're going to see the text that we're going to use to construct our knowledge graph. So it's this text here. If you want to use, you can use your own text if you want to, but this is the text we're going to use for this example. We have a piece of text here about the main character from the movie Dune. So Paul Atreides. We have some information about his parents, the planet he rules, and the organizations his mother is a member of. Okay. So as I said, the first step in constructing our knowledge graph is typically to chunk up our text. So once again, we're going to use the text splitter from our package. We're going to use the fixed size splitter again. This time we're going to use a chunk size of 150 and a chunk overlap of 20. So we want to copy this piece of code into our IDE here. The next step is to create an embedding for each chunk. Again, we're going to use the same code we used in the last challenge for this. We're going to use OpenAI to create our embeddings. I'm going to use the same model here. So we're going to copy this again across to our file here. Next, to guide our LLM, we want to list types of entities and relationships we want to extract from our text, as well as how those entities and relationships fit together. So this means that our LLM won't just extract any old information from our chunks, but we'll just extract the information that we're looking for. So in this piece of text, what we want is we want the LLM to look for people, houses, planets, organizations, and we want to look for relationships such as, one person being the son of another person. You can see that here. One person being the heir of a house, a house ruling a planet, and a person being a member of an organization. So these are the sorts of relationships and entities that we want our LLM to extract. So copy that over to our IDE again. Now we add an LLM to extract entities and relationships from each chunk. So here we're going to use GPT-4o, and we've set a few model parameters here just to ensure that this process is as kind of repeatable as possible. Finally, we want to create our knowledge graph creation pipeline. We can see here what we're feeding. We're feeding our pipeline, the text splitter, our embedder, the entities, relationships, and how we want those entity relationships to interact with each other here. We're feeding our LLM. We're just telling it that we want, if it encounters an error, we want to ignore it. And we're not running from a PDF, we're running directly from text. And we're also feeding our Neo4j driver into this. So this is our pipeline here that we're going to run to create our knowledge graph from our piece of text. Finally, the last part is to run our pipeline on our text. So we use this piece of code to do that. Instead, we're running this on a piece of text about one of the characters from the Dune franchise. So let's see this running, and let's see what sort of knowledge graph we extract using our pipeline. So we copy and paste this in here, then run our example. You should see some information prints out as it does things like create embeddings and chunk up the text. Okay. Once you see pipeline finished, that means we're done. Let's go back to the course here and see our graph. So we can run our Cypher query here to see our knowledge graph. It should look something like this, but it's not guaranteed. LLMs, are not fully deterministic, so it might look slightly different for this, but hopefully we should get something at least somewhat similar to this. So yeah, we do. So we can see some of our entities have been extracted here. So if we scroll back up to our schema, like I said, we were looking for person entities. So we've extracted a few of those. So this is a person entity. We've extracted Leo Atreides and Paul and Lady Jessica. These are people. We were looking for a house. We found House Atreides. A planet. We found Caladan. And we found some of the relationships we were looking for as well. So we can see here that Paul is son of Leo Atreides. We can see that House Atreides rules the planet Caladan. And we can also see the chunks that we extracted. So this is the first chunk here. with our embedding. Second chunk here. Again, this is the embedding. This is the text of the second chunk. So finally, just a bit of a bonus challenge for you all. If you want to complete this after the workshop is over. You've seen in some previous lessons how you can create vector and full text indexes. See if you can do this with the chunks here. So we have some chunks. See if you can create indexes for these chunks and see if you can search them. And with that, thank you for paying attention. Hopefully you learned something useful in that first section. I'm now going to hand you over to Will, who's going to take you through how you can use some of the stuff you've learned here to build a RAG application. So over to you, Will.
Cool. Before or while Will is getting ready, we had a question or two in the Q&A panel. Maybe Alex, we can quickly read that and look at those. One comes from Julian. Julian asks, can we have hybrid extraction with some entities matching the schema and some others flagged as others that do not match the schema?
Yes. So what I showed you here is the simple, sorry, this is the wrong one, build graph. If I go back to it, this is the simple KG pipeline for building the building knowledge graphs using our package. And I showed you the most basic version of this, but we have you are able to do things like strictly just extract the entities and relations that you want. So if the LLM finds anything else or any other properties, it will throw away that data. You can do you can not provide these entities, relations, and schema, and the LLM can just find whatever it finds and create a knowledge graph based on that. Or you can do this sort of optional thing where you want to maybe say find, I'm looking for these entities, but if you find anything else, add that to the knowledge graph. These sorts of options, I don't believe they're in our current release of the package, but they should be in the next release. So more varied options for how you want to extract entities and properties and relations from a piece of text into a knowledge graph. So yeah, yes, the answer basically in general, you do have a lot of options here. This is just a very basic example.
Super cool. I think that also answers Job's question. Job asks, what if you want to build a knowledge graph from data, but you don't know the entities or relationships involved yet? So I think, yeah, what you just showed, I mean, you can start with defining a couple and then add to it as you go, or expand on your initial set, basically.
Yeah. And I'm just seeing Gillian's question here for entity relations. Do you have to use the GDS? No, you don't. You don't have to use the GDS library for this.
Cool. All right. Think that is all that we had for now. So I'll thank you very much, Alex, for the first part of it, and handing it over to Will.
Thank you, Alex. I'm just going to share my screen. And yeah, good job everyone for making it through part 1. So yeah, now we're going to take a look at the second part of the course. And this one is going to be a little bit more hands-on. So what we'll do today is we are going to use the same environment. So whether it's code space like before or your local environment, we're going to try out the different retrievers in the GraphRAG package. So we're going to try out 5 different retrievers today. And then at the end, we can we'll tie everything together with a multimodal application that combines textual and visual data. So yeah, if everyone is okay, we can move on. So yeah, going to go back on what RAG is. So yeah, as you know, the course today is mastering retrieval augmented generation. But what exactly is RAG? So RAG stands for retrieval augmented generation. It combines retrieval-based methods with generative language models, which is where the name comes from, to enhance response quality and accuracy. So what does that actually mean? And the keyword here is search. So imagine whenever you prompt an LLM to give you an answer, it first searches over a database before actually returning the answer to you. So by doing this, you can try to ensure it generates responses that are contextually relevant and also factually correct. And this provides two benefits. If you notice here, the LLM does not even have to have seen your data before, meaning your private data can stay private and not be included in whatever LLM you use. Secondly, it's a neat alternative to fine-tuning the data on the LLM, which again means your data stays private. And yeah, so it turns out Neo4j is very effective for RAG. And yeah, now I'm going to show you how to use our GraphRAG Python package for RAG. Let's go to the next page. Okay. So yeah, I mentioned we're going to look at 5 different retrievers today. The first one is we're going to start taking a look at the vector retriever. It's the most basic one where you can search over a vector index. But in our package, we have different types of retrievers that you can select for different types of use cases. Here, the vector retriever searches over a vector index. So if you remember what a vector index is from the first part of the course, you can basically convert your unstructured data into a vector embedding and then store them in a database. And then after you store these vector embeddings in a database, you can create a vector index over your vector database, over your vector embeddings, which allows you to search over them very efficiently. So let's say there's an incoming query text, and then you convert this query text into a vector embedding. You can use our package to then retrieve the top K most similar vector embeddings to your query embedding that is in the database. And that corresponds to the most similar text. So yeah, well, what does that mean? It's important to remember that by searching for the most similar vector embeddings or the close vector embeddings, this corresponds to 2 texts being close in meaning or semantically close. And let me see. So yeah, you not only can, so the important thing to note is you not only can create these embeddings from text, you can create it for any unstructured data. So yeah, this also applies to images, videos, any kind of unstructured data. So let's look at a more practical example now. So yeah, if you open up your code, I want you to go to the assuming everyone's environment is set up correctly. You can go to the vector retriever file here, and yeah, we're going to do 3 things now. So to use our package, especially for using the retrievers, it's kind of 3 main things you need to do. So the first thing here is we need to define initialize our embedder. So this is how we actually embed. In this case, we're going to be using query text into vector embeddings. So here I've defined, so yeah, there are different types of, we support various embedding methods or embedding classes. Here, because before we have populated the database, populated vector embeddings of movie plots using this specific OpenAI model, so text embedding Ada2. So we're going to use that here. So yeah, here we're going to define that this is our embedder. Just going to paste this here. Yeah, and everything prior to this is just setting up the database. So yeah, this connects the Neo4j database. We've now set up the embedder. The second thing we need to do is set up the retriever. So here using the vector retriever. And I'm going to talk about this. So when defining the retriever, especially the vector retriever here, we specify the driver. The driver being how we connect to the Neo4j database. We specify the vector index name here. So in this case, it was the name of the index we created in the first part, which is movie plots. So yeah, by searching over this vector index, we'll be searching over the embeddings of the movie plots. So the third thing we pass in is the embedder that we define here. And there's another parameter here, which is return properties. So here we can try to make the output a bit nicer. So yeah, we only want the title and the plot node properties from the graph. I think if we don't specify this, it will return like everything. Okay, so that's the second part. For the third part, we will actually use the retriever. So in the package, we provide a GraphRAG object. Sorry, and yeah, an OpenAI LLM object. So this one, maybe I'll highlight like this. OpenAI LLM object is different from this OpenAI embeddings object. So this is like the object to embed unstructured data. This is for generating outputs from the LLM. So here, we're going to use GPT-4o. You can specify the model parameters as well. I've set temperature to 0. And then we define this GraphRAG object where we pass in, so RAG, so it's retriever augmented generation. So we need to pass in the retriever, and we need to pass in the LLM here that's going to generate the text first. And from this point, it's easy. So we call the .search method. We call a search method for the RAG object. And then we pass in the query text. So here I've asked, give me 3 films where a hero goes on a journey, and retrieve the top 5 most similar movie plots. So I'm going to run this. So yeah, I've asked it to return the title and the plot, so it should return that. Okay, so in our case, let's see what it generates. So first one is the Wizard of Oz. And then yeah, it returns both the title here and the plot. Second one is Last Action Hero. I've not seen this one. But looking at the plot, it sounds like what we're looking for. Third one is Never Ending Story 3. And yeah, looking at the plot, it looks like something we're after as well. So yeah, very nice. We've successfully used the vector retriever to first do a vector search over the vector index of movie plots, and then return both the title and the plot. So that's very nice. And some tips for using this effectively is, yeah, you have to make sure you use consistent embedding. So make sure you use the same model for both query and incoming query and existing node embeddings to ensure compatibility, because it doesn't make sense to search over a different embedding space. It only makes sense to search within the same embedding space. You can utilize arguments such as return properties. Oh yeah, there's another argument called result formatter to retrieve and transform the desired properties from the graph effectively. And the third tip is, we'll experiment with the top K parameter, because it's important to note that this retriever uses an approximate nearest neighbor algorithm. So you can consider setting top K to a higher value to improve the chances of retrieving relevant results. And this doesn't mean, because basically this is not exact nearest neighbor search. And I think this is like a more practical tip. So that's the vector retriever. I'm going to move on to something a bit more interesting now. It's called the vector cipher retriever. So at this point you might be asking, how can I actually leverage my Neo4j graph for this? And this is where the vector cipher retriever comes in. So using this retriever, you can combine the previous vector retriever with Cypher, which is the query language for Neo4j. So
Will,
yeah,
sorry to interrupt, but we had a calendar invite issue where now we had a bunch of people join late because I think time zoning was somehow mixed up the initial start. So I just asked, or Dennis actually made the suggestion if Alex could give a quick 5-minute or a couple of minutes quick recap of what we talked about in the first hour to get everybody up to speed, so then everybody could still follow what you will be talking about without having to drop off.
Okay, sounds good. I'll pass it to you, Alex.
So is it all right if I just quickly share my screen again? Let's see. Okay. Okay, yeah, apologies for the calendar issue. So basically in the first, we've been following, for those who missed the first half, we've been following along this Graph Academy course here, the Mastering Retrieval Augmented Generation Graph Academy course. So if you scroll to the top of the chat section, you should see a link to this course and also an OpenAI key, which we've been using throughout this course. So in the first half, basically we covered the first half of this course, where we talked through how we talked through some of the sort of the basic concepts in RAG. So for example, we covered vectors. So we talked about how vectors can be used to represent pieces of text and images, and kind of what vectors are. We talked through embeddings models and how we can use embeddings models to create vectors for our text and images. And we talked through semantic search, how we can compare embeddings to find pieces of text that are semantically similar to one another. We also went through a little bit here. There is, sorry, I probably should have covered this first. There's a section here for setting up the development environment. So the stuff that Will was going through there on the vector retriever, he was using a development environment that he had set up here, following these instructions. So it should be fairly straightforward, but you can follow along with these exercises on your local machine, or you can use a GitHub CoSpace. So back to the content, we also covered how we can create a vector index in Neo4j. So we went over creating an index on a property in a movies database. We went through how we can create embeddings, and how we create embeddings and use those embeddings to search our vector index. We went over how we can create a full text index, what full text search is, how it differs from semantic search. So full text search being where we're looking for keywords in text rather than semantic meaning. So for example, we might be looking for specific things, specific strings like a year, like 2019, or specific keyword terms like specific characters in a movie that might not have semantic meaning outside of that movie. And how we can use, we can also search over full text indexes in Neo4j. We covered a little bit about unstructured data and how we can use knowledge graphs to represent that unstructured data. How we can chunk up that unstructured data, and we can use we can create embeddings from it. And then finally, the last section, we covered how we can use the Neo4j. So we covered a little bit more about what knowledge graphs are. And then we covered how we can use the Neo4j GraphRAG package to create knowledge graphs from unstructured data. So the process here is basically taking some unstructured data, chunking it up, creating embeddings from each of those chunks, using an LLM to extract entities and relationships from each of those chunks. And we guide the LLM using a schema here. And then uploading all of that. So yeah, we use it, like I said, using an LLM, and then uploading all of that to our Neo4j database to create our knowledge graph from this piece of unstructured data. So this was kind of this was kind of one of the first hands-on exercises. So it's worth following along with, or trying maybe after the workshop is over, just to see how you can use our package to create graphs from unstructured data. So how you can take your unstructured data and actually get it into Neo4j in a useful way. And now what Will is now covering how we can use our package, use the retrievers in our package to query our data. So hopefully that was a sort of good enough summary of what we covered in the first half. I think this is going to be recorded, so you should be able to go back in your own time and see it in more detail. But I don't want to take up too much of Will's time, so I will pass back to you, Will.
Thanks, Alex. Show my screen again. And yeah, apologies everyone for the calendar issue, but yeah, for the purposes of running the rest of the code, just ensure you, just ensure you have like your environment variable set up correctly. So yeah, I'll just quickly point out that the OpenAI API key we're using should be pasted in the chat. And for the other parameters, so for example, like the Neo4j parameters, you should be able to find it in the, I think, the second page of the course. So setting up your development environment. So in my case, I found mine. Yeah, I got mine from here. And then I basically just pasted in these into these environment variables. There should be an example on here so you can see like, which environment variables are needed. And yeah, if you are able to run this vector retriever example, then it should be okay, I think. But yeah, let me know if people have issues. Okay, so yeah, continuing on. Just to recap, what we did earlier was we took a look at the vector retriever. So yeah, just searches over a vector index, like what Alex said. Converted text, in this case our movie plots, to embeddings, put it into the database, build a vector index over the vector embeddings, and then we can do search and then RAG. Now we're gonna look at, where is it? second bit, which is doing a graph traversal with the vector retriever. So there's an object called a vector cipher retriever from the package, and if you can see this cipher snippet here, we can run it in the tool on the right here. So what this query does, if you can see carefully, this matches all movie nodes that has the title property. That has the title Jumanji, and then it also matches all actor nodes that have acted in the movie Jumanji. So here in the round in this brackets, it's the node, and here we specify the relationship that links to this movie node. And finally, we return the movie node, and then we collect all the actors as actors. So if you see here, I'm just going to zoom out a bit. Yeah, we got our Jumanji node, and then we got all the actor nodes that have acted in this movie. So in our case, it's Kirsten Dunst, Bradley Pierce, Jonathan Hyde, and Robin Williams. I've not seen the movie in a while, so let me know if that's incorrect or anything. Gonna dive deeper into the vector cipher retriever. How it works is we combine the knowledge of our graph with vector retrieval, and then we can apply an additional cipher query to filter the nodes based on our query. So we apply this cipher query afterwards to filter nodes based on your query, basically. Let's take a look. Actually, I'll briefly talk about when we want to use this. So you would typically want to do this if, let's say, you understand your graph structure and you want to leverage some kind of structure in your graph. So you can combine both the knowledge of your graph and similarity search. But otherwise you can just use it in the same way as before. So let's look at it in code. So open up the vector cipher retriever example. Again, it's going to be 3 steps. So the first step is you initialize your embedder. So in our case, it's going to be, again, OpenAI embeddings, because now I want to search over movie plots, which was embedded using the OpenAI model called Text Embedding 8.2, same as the previous example. I'm going to copy and paste it here. So we've initialized our embedder. Now we're going to initialize the retriever. I'm just going to copy and paste. And I'll explain it now. So here for the vector cipher retriever, a little bit similar to before, but there's a bit of a difference. So like before, we provide the Neo4j driver, which is defined above. This is how we connect to the Neo4j database. So we pass in the driver, we pass in the vector index name that we're going to search over. In our case, it's movie plots. This would have been created in the first section of the course, by the way. So if you've not done that, we just double check that. Then we pass in the embedder. So it's the embedder we define here. And then the thing that's different is we pass in the retrieval query. So here, it's similar to the one I showed you earlier. So here we actually have a node called node. It's assumed that the results from the vector search are in node, basically. And then here we define a cipher query to be, get all the actors that have acted in this node, which is it's basically the retrieve nodes for from the vector search. In our cases, the movie plots. As in the nodes returned from the movie plot similarity search. So here finally want to return the node.title, node.plot, and then also all the actors. So collect actor.name. So that's the retriever object. Finally, in the third part, same as before. So this one I think is exactly the same actually. We define our LLM object, which does the actual generation, text generation. In this case, it's GPT-4o. The GraphRAG object, which requires the retriever object and the LLM object. And then, yeah, we're going to call rag.search now. So in this example now, we pass in the query text, who were the actors in the movie about the Magic Jungle board game? Let's run this. Okay, yeah, so and what gets generated is the actors in the movie about the Magic Jungle board game, Jumanji, are Robin Williams, Bradley Pierce, Kirsten Dunst, and Jonathan Hyde, which thankfully are the four ones here. So yeah, what our LLM, well, what our code managed to do is first search of a database, found the Jumanji node, and then it gets all the actors that have acted in that movie, and then finally returns and generates something meaningful. So yeah, that's the vector cipher retriever. It's particularly, I find it like a very useful retriever actually. And some tips for using this effectively is it's important that, yeah, like before, it's important that both the query embeddings and the stored embeddings in the database are generated using the same embedding model. In our case, it was text embedding ADA2, because it only makes sense to search in the same embedding space. And like before, we can utilize result formatter to retrieve and transform the desired properties effectively. And most importantly, if you understand how your graph database is structured, you can fully utilize this retriever because you can leverage your cipher proficiency to query the relevant data as context for the LLM. So yeah, just want to see if there are any questions so far regarding the vector cipher retriever. Okay, no, nothing yet. So yeah, I'll move on to the next bit, which is going to be the hybrid retriever. So yeah, we've covered the vector retriever, covered the vector cipher retriever. I'm going to talk about the third one now, which is the hybrid retriever. So if you remember from previous section, we didn't only just have a vector index, we also had something else. So there's another index we had called a full text index. And the full text index is different from the vector index. The full text index leverages full text search. So it basically does keyword matching. Oops, sorry. Sorry, there's a bit of a thing going on. Okay, sorry about that. Yeah, so not only we had a vector index, but we also had full text index. And yeah, a vector index does similarity search over, yeah, vector embeddings. A full text index does keyword matching. So you can actually use both. So in a hybrid retriever, you now not only use the vector index, but you also use the full text index that you can search over. And then, yeah, it's illustrated here in this graph. So vector and search, full text search. It returns nodes from both searches, and then it does some like sort of like normalizing, and then it reorders search results from both indexes, and then sort of reorders them by score, and then finally returns the top k nodes. Hope that makes sense. I'll show you an example quickly. Yeah, before that, when would you want to use this? you want to use this when your data is diverse. So for example, like, it's not enough to just do similarity search, but there are a lot of keywords which are for example, like very important to search over, or maybe like the LLM does not have context of those keywords. In those cases, you want to use this hybrid retriever, as opposed to just searching based on semantic similarity. So yeah, let's look at code. Open up the hybrid retriever file. So yeah, like before, 3 things you need to do. Here again, yeah, we're defining the embedder, which is the embedder for the vector search. Text embedding ADA2 again. And then we're going to initialize our retriever. So I'm going to talk about this in a second. So yeah, like before, we pass in our driver, which connects to the Neo4j database, the vector index name. So this is what, we're going to search over movie plots again. And the full text index name. So now we want to do a search over the full text index called plot full text, which, if you're not sure, it should have been created in the first part of the course. So yeah, if you go back to one of the previous parts of the first part of the course, there should be a Cypher query that actually creates this full text index. It's called plot full text index. So yeah, now we've defined both our index names. We also, like before, we pass in embedded objects and also pass in return properties. So I only want title and plot properties of the node that are returned. So yeah, in this third part, we're going to, like before, we're going to actually use the retriever. So yeah, we pass in the LLM object into the GraphRAG object again. So we're using the exact same LLM object and GraphRAG object. And then we call rag.search. So now query text, the incoming query text is going to be, what is the name of the movie set in 1375 in Imperial China? So yeah, in our case, like it's quite unlikely that our LLM has like context to sort of like associate semantically 1375 and like the movie you're going to search for. But I'm just going to run this to show you. So, okay. Yeah, sorry. If you do receive this warning, it's probably because in my case, I've not updated to the latest version of the package. But yeah, if you want to get rid of it, you can just update it. But yeah, the result of the answer is the name of the movie set in 1375 in Imperial China is Musa the Warrior Musa. And yeah, this is correct. And what's interesting is if you pass this query text to the vector retriever, so this going back to the first one, I'm just going to run this. So yeah, in this case, because it only does a vector similarity search, it's unable to find it just based on the plot. So yeah, using the hybrid retriever, because there's this keyword 1375, maybe you want something specific like a keyword, then yeah, in this case, because you're able to search over it in the full text index, you can actually retrieve the relevant movie. So yeah, when would that actually be useful? For example, if you have like a lot of like technical terms, maybe like a certain like molecule name or like some technical thing or some specific engineering part, you could use the full text index quite efficiently. In tips of effective use, again, make sure you use consistent embeddings. to ensure compatibility. And then, yeah, make sure you're actually using the full text index here. So yeah, you can search over relevant properties to enhance, keyword search basically. And yeah, that's basically it for the hybrid retriever. Now we're going to move on to the fourth one, which is the hybrid retriever, but with graph traversal. So now we're going to introduce this object called the hybrid cipher retriever, which is very similar to the two previous retrievers. So basically, this is the hybrid retriever, but with, you can use cipher. So let's try writing this cipher command in the sandbox, yeah? So what this does is it gets all the movies with the title Musa the Warrior, Musa. And then it fetches all the actors that have acted in this movie, and then finally returns like the movie node and then all the actors. So as you can see here, 4 actors: Jim Ju, Sung Ki-an, Ji Zhang, and Irfan Khan, and that have actors in this that have acted in this movie. We're going to see it in action later. So I'm just going to show you how it works. Somewhat similar to the previous one, except, so yeah, here you do your vector search, do your full text search, and then you combine and reorder them by score, and then you get your top key nodes. And then at the end here on the right, as you can notice, for those observant, you have an additional thing. So you augment your nodes with graph traversal. So using the cipher query, you also return like additional information from the hybrid search. So yeah, basically sort of 3 steps: hybrid search, graph traversal, and then aggregation. When you want to use this, so this is a bit more of a complex one. When you get complex queries, so you not only want to leverage semantic search and full text search, you also want to be able to capture like rich data relationships in your graph. And yeah, this helps with being able to provide precise information to your LLM for RAG by searching using both search methods and also like leveraging the graph structure. So let's take a look at code. So I want you to open up the hybrid cipher retriever file. And same as before, 3 parts. So here, embedder for embedder that you use for creating the vector embeddings. Now we're going to initialize the hybrid cipher retriever. The second part, I'll copy paste. So here, as you can see, it's very similar to the vector cipher retriever. So we pass in the driver, except now we provide both the vector index name and the full text index name. And then finally we provide the retrieval query. So yeah, this is similar to the one we saw earlier, which we want to get all, well, first the hybrid search does, it retrieves the movie nodes. So here we call it nodes. And then what the retrieval query that gets appended onto it is, we get all the actor nodes that have acted in those movies, and then finally return node.title, node.plot, and all the actor names. Pass that retrieval query into the retriever, and like before, we pass in the embedded object. And now we can do our RAG. So I'll copy paste this. So like before, we have our LLM object that is GPT-4o. GraphRAG object, we pass in retrieve an LLM object, and then we call rag.search. So our query text now is a bit more complicated than the one before. So before was, okay, what movie was set in 1375 in Imperial China? Now we also ask what are the names of the actors in the movie that is set in 1375 in Imperial China. So yeah, again, get the top K. In this case is 5. Let's run this file. So yeah, like I said before, if you get this warning, please update to the latest version of the package, which I've not done. But yeah, otherwise you shouldn't see it. So yeah, the output is the actors in the movie Musa the Warrior Musa, which is set in 1375 in Imperial China, are Irfan Khan, Zi Zhang, Sun Qian, and Jin Moju. Okay, that is exactly what we saw here. Very nice. So yeah, just from this query text, we're able to, well, what we first did was using hybrid search, we got the relevant movie. And then using the retrieval query, we got the actors. So now we can provide like a comprehensive answer. And yeah, maybe you might be interested to compare it with, how this would have worked if it's just a vector retriever, because yeah, let's take a look. So now, yeah, I'm just using similarity search here. Let's see if the LLM knows this. So yeah, here I'm sorry, but I don't have information on the movie. Yeah, set in 1375 in Imperial China. But if we use the vector retriever, this would not have worked. But if we use the hybrid cipher retriever, this worked very nicely. And yeah, that's it for the hybrid cipher retriever. Just some tips for effective use. Similar to before, use consistent embeddings. Make sure you use your full text index correctly. Because yeah, full text index, you can leverage keyword matching basically. And similar to the vector cipher retriever, you can leverage cipher proficiency here. So yeah, this of course this assumes like, okay, you know how your graph works. But then yeah, if you do know that, this is a very powerful retriever to use. And yeah, using cipher, you can maximize the effectiveness of this retriever. Okay, so we've covered 4 retrievers. Now we're going to cover something a little bit more interesting. So there's a 5th retriever here we're going to cover. It's called the text to cipher retriever. It's going to look a little bit different from the retriever, but the previous retrievers, but yeah, it's still a retriever. Let's say you don't want to manually write out your cipher statements. So of course, like before, let's assume you know how your graph works. But you don't want to, like in this case, you don't want to manually write out the cipher statements. What you can do is you can get an LLM to do it for you. So this LLM, we call this text to cipher. Well, this process we call text to cipher. So here, okay, on the left, there's query text. Well, not query text, but on the left, there's text that you pass into the text to cipher model. And then, okay, you want it to write a cipher query that returns the first 25 nodes from the graph. What that means in cipher is this query here, so match and return and limit 25. And yeah, what it's doing here is converting natural language into cipher queries. And yeah, we have a retriever for this. It can be very useful. So I want you to try running the cipher command in the sandbox. So what it's doing here is it gets all the actors with name Hugo Weaving that have acted in these movie nodes, and then return all the movies. Return the movie.title as movie title, and then also return movies. So yeah, there are 8 movies here. These are all movies that Hugo Weaving has acted in. So yeah, The Matrix, The Interview, V for Vendetta, Babe. Yeah, we're going to see this later. So yeah, just before I show you code, I'll talk a bit about when you want to use this. So this simplifies a lot of what we talked about earlier. So yeah, you maybe want to use this for simplicity. You can avoid manually writing out cipher. This retriever also provides more of a natural interaction, which allows users to interact with the database just using natural language. and it's more accessible if you don't, if you're not an expert in Cypher or anything like that. I think it's important to mention, obviously LLMs are non-deterministic, so yeah, the output of text cipher LLMs can also be unpredictable sometimes. So yeah, if you do not set it up right, you can still run into errors where the LLM generates like invalid cipher. So use this with care, I would advise. Okay, so let's look at some code. We should open the text cipher retriever file. So here we have two parts. So like before, we set up the Neo4j database connection. So, okay, let's copy this and I'll explain. So here, what we're doing now is we import the text to cipher retriever. Here we need to create the LLM object for text to cipher. So in our case, we're using GPT 3.5 Turbo to generate the cipher. And yeah, this is not the only one you can use, by the way. And if you check our documentation for our package, there's a whole bunch of LLMs you can use. And here we provide the Neo4j schema. This is optional, but of course, if you know LLMs, more context is always very helpful. So here we provide, as additional context to our text cipher LLM, the Neo4j schema. So yeah, we know. So this one I knew beforehand, so I can provide like, okay, for our graph database, this is a very useful schema. If this is the schema that we use, so this person, movie, I specify the types, the relationship properties, and yeah, these are possible relationships. And then I provide some examples as well. So here, okay, if the user inputs which active star in the matrix, this is like a possible cipher query. Now we actually want to build the retriever. So, okay, we have text to cipher retriever. We pass in the driver like before. So this connects the Neo4j database. We pass in the text to cipher LLM, pass in the schema, pass in the examples. Nice, we've set up our retriever. Okay, let's look at the second part, which is actually using this. So this one will look very similar to the one before. So we define the generation LLM. So in our case, we're going to use GPT-4o again. We have the GraphRAG object. And like before, yeah, the GraphRAG object, we pass in the retriever like before, and also the generation LLM. And then we're going to call rag.search. So yeah, the query text will be, which movies did Hugo Weaving star in? Let's run this. Okay, so yeah, the answer from the generation was Hugo Weaving star in the following movies: Cloud Atlas, The Dressmaker, Babe, yeah, and these other films. And if you can count them, 1, 2, 3, 4, 5, 6. Okay, how many is that? I might be miscounting. But yeah, these are films from here, which is very nice. And yeah, in this example, of course, it makes it like very simple. But yeah, I would advise like use it carefully, because yeah, like any LLM, the text to cipher LLM can be unpredictable. It's not non-deterministic by definition. So yeah, you use it carefully, but yeah, it's also a very powerful retriever to use. Yeah, so some more tips for effective use is, make sure you provide a clear Neo4j schema to improve query accuracy. and supply example queries, and be prepared to handle errors because the text cipher model could generate invalid cipher. Okay, so we have covered 5 different retrievers. The final bit here is we're going to look at a practical example. So in our case, we're going to look at the vector cipher retriever. And yeah, just to recap briefly as well, we've covered 5 different retrievers. Each of them sort of has the different use case. And then now we're going to look at an example where we search over images, but return movie titles and movie plot, etc. So let's run this command. Okay. What the cipher doing here, what the cipher command is doing is it gets all movie titles with, well, it gets all movies with this title, Homeward Bound: The Incredible Journey. And then it gets all the actor nodes that, well, it gets all the actors that have acted in this movie. And finally returns the movie node and all the actors. So yeah, you can see here, this is the movie we were looking for. And then, yeah, there are 4 actors here. Okay, so I want you to open up this multimodal app file. It's going to be 2 things we need to copy and paste. So for the first one, it's like before, we initialize the embedder. But yeah, in this case, you may notice because we want to search over image embeddings this time. And the image embedding model we used was this OpenAI model, I think. Oh, no, sorry, this is not OpenAI. I think this might be from Sentence Transformer. So this is ClipVIT-B32 model. And then here, instead of using OpenAI embeddings, we use Sentence Transformer embeddings. And then this is how we define embedder. So yeah, copy paste that to here. And then now we initialize the retriever. So copy paste this, and I'll explain in a second. Just close this. So yeah, like before, we have the embedder. We have to specify, yeah, if you look closely at the vector cipher retriever, like before, we need to provide the driver. We need to provide the index name. In our case, the index name is going to be movie posters. So we should have, I think if you were following the first part of the course, you should have created the movie posters vector index. There should be a cipher command somewhere for that. So yeah, if you haven't done that, please go do that. So yeah, we provided the index name. We provide this retrieval query now. So let's look at the retrieval query here. So yeah, like remember, like the retrieval query is like a cipher query that gets appended from the results of the vector search. So the results of the vector search, yeah, assuming we've done like, our similarity search, we found like the most similar nodes, or in this case, like movies that are most similar in terms of like the, in the movie poster space. The retrieval query now, okay, we get the node.title. So in this case, like the movie title, the movie plot, and also the movie poster. Yeah, so you can take a look at the images later. And finally, the score, which is the vector similarity score. So previously, yeah, so that was the retrieval query. Now we're going to provide something called result formatter. So previously we had, another argument that passes the output. Here we're going to use result formatter instead. So this sort of like just makes the results from the query in a much more structured way. So yeah, here we define a format record function that returns retriever result item, and then it takes in a Neo4j record. So that's sort of like the query results, and then formats them into something more structured. So pass that format record function to result format here. And yeah, we have now successfully defined our retriever. So now we're going to actually use it. So yeah, here we call retriever.search. I'm going to pass in query text, find a movie where in the poster there are only animals without people. And yeah, top K equals 3 here. And then yeah, I'm going to print the results here. So let's take a look. I'm going to run this app. And yeah, if you're running this for the first time, it may take some time to set up like the sentence transformer embeddings and everything. I ran this once before, so yeah, mine should be a bit faster. But you might see like, okay, some setup being done. Yeah, and by that I mean like, okay, because we're using sentence transformer embedding. Sentence transformer is an open source Python library. So we're using embeddings from there. Not in this case, we're not using OpenAI embeddings actually. Just gonna let this run for a while. But yeah, is there anything specifically to this example that's unclear for anyone? Okay, so yeah, we have our results. Yeah, specify top K equals 3 here. So yeah, we have 3 results. And the first one is, okay, they gets returned Apollo 13. Okay, I asked for a movie in a poster where there are only animals without people. Let's take a look at the image, actually. So if you click on the link, it should open. Okay, in this case, it doesn't look like there are any animals, actually. So yeah, it's possible that, okay, maybe the image embedding model got a bit confused. But for me, it does look a bit like ambiguous, I guess. Maybe, yeah, the model is just not good enough to detect that, you know, there are actually just no animals here. Let's look at the second one. Free Willy. Movie plot: when a boy learns that beloved killer whale is to be killed by aquarium owners. Let's take a look at the poster. Okay, you can see that there's an animal here. Yeah, there's still a person here. So maybe the image embedding model was just not as like, didn't manage to capture that nuance. But yeah, you can see there's an animal. So I guess that's kind of a pass. The third one, movie title, Andre. Movie plot: the true story of how a marine sea lion named Andre befriended a little girl and her family. Let's take a look at the poster. Okay, yeah, there's an animal here. A very cute looking one of that. And okay, there's a person here, but yeah, I think it's probably in our case, like the model we used was just a bit, I guess, didn't manage to capture that nuance. But yeah, I think 2 out of 3 of those had animals. But yeah, you can feel free to play around with this, ask the different types of questions. But yeah, I think it's pretty cool that you can do this. You can, search over images and then actually return information from your database that are related to that image. So yeah, going back to the course. Yeah, here I mentioned some additional tips as well. Yeah, make sure the image embeddings you use. In our case, it was the sentence transform embeddings. Make sure it's consistent. Make sure it can accurately capture visual features of the movie posters for semantic similarity. Make sure you're using the correct vector index. So in this case, it's movie posters. And yeah, what we did here was because within our database we had we were able to like, link images and text. So here we can have like a multimodal integration, which I think is pretty cool. Okay, so that was it for the multimodal app. Congratulations, you have successfully completed this workshop. Yeah, just to recap, we've covered 5 different retrievers, which you can use for different use cases. So the vector retriever, the vector cipher retriever, the hybrid cipher retriever, and the text to cipher retriever. We showed how you can build a multimodal application that integrates both texture and visual data. And you have learned that how you can enhance your GraphRAG application with the Neo4j GraphRAG package. And so yeah, just to recap as well, there's like a table here to show when would you want to use each retriever. So yeah, feel free to take a look at this table. And yeah, hope you can build something interesting and useful with our package. Thank you very much, and I'll pass it back to Alex.
Super cool. Thank you very much, Will. Thank you very much, Alex. Again, sorry for the confusion and the issues with the time zones for the calendar invite. Very, very sorry. I don't know. We will investigate to make sure that doesn't happen again in the future with our coming workshops. We had a couple of questions, and I think we are already over time, so I don't want to take too much time away from everybody, but I think 1 or 2 would be good to answer in public, so everybody kind of gets on the same page. And one is that came up, I think 2 or 3 times, is obviously we use OpenAI's toolage here for this workshop, but if you want to do it yourself, if you want to do it on your own, continue working with an LLM, but don't want to use OpenAI, do you have other options, maybe even local LLMs to work with the retrievers?
Yeah, it's a great question. So for our package, we do support quite a few LLM providers. So not only OpenAI. If you look at our documentation, where is it? Yeah. So yeah, we have a whole list here somewhere. So yeah, if you go to the embedded section here, we not only have OpenAI embeddings, we also support embeddings from Sentence Transformer, Azure OpenAI, Ollama, Vertex, Mistral, and Cohere as well. And yeah, this list continues to grow as well. So yeah, feel free to take a look.
Super. That's great. There was also a question that came up 2 times now for the one that you just showed last, and then also for the text to cipher embedder, is how about debugging mode when you want to see what actually is being created to see if it needs fixing, or if it can be fixed with looking at the created text.
So from what I recall, there should be an option for that. I can't remember which exact arguments there are. But yeah, I would say try and take a look at documentation and yeah, see how to do that. And yeah, if you can't do that, we're open to questions as well, or issues. Feel free to check out our repo.
Yeah, cool. So I think that's where is it here? I think let me quickly put that. Yeah, here it is. Let me put that in chat. What you just open here is the GraphRAG Python package, and you find the full documentation and everything there, and have kind of a look at it. The other thing I want to link to everybody in chat is our developer guides on the GenAI ecosystem, and specifically about GraphRAG. There are lots of GraphRAG examples, lots of other demo applications, how to import data and how to work with data, how to build a knowledge graph. Obviously, the whole Graph Academy, like the course you just seen here today, but there are also more courses on our Graph Academy curriculums, basically, where you can learn more. If you are interested in the whole, staying up to date, what's happening in the AI space, I think MCP is the word of the hour. And we are having a MCP webinar coming up in, well, actually next week. Everything a developer needs to know about MCP, so Model Context Protocol, happening on the 10th of June with Michael Hunger and Zach Blumenfeld from our product team, and they give you a current status of things, how to use MCP together with Neo4j. So I think that's also going to be an interesting session coming up. Again, as I said in the beginning, we have recorded this session. We will share the links to the Graph Academy course that we just ran through to you via email, and also the link to this video, so you can recap and catch up on things that you might have missed. Thank you very much. Is what leaves me. What I'm left to say. Everybody, thank you for joining. Thank you, Will and Alex, again for guiding us through, for helping with questions, and for presenting, obviously, the workshop today. I think it was very informative, very, very good, and thank everybody for joining. Thank you for spending the time with us this morning, and thank you for your questions and comments. And yeah, hope to see you on one of these next ones. Yeah, until next time. See you soon. Bye.